Schoen for the Radó Lectures. And right now he's chair professor in Irvine after almost 30 years, something, in Stanford.
Yeah, about that.
So I was fortunate to spend some time in Stanford with Rick, and I asked him if I could claim to be his postdoc. He said yes. So for that, I'm very grateful. Over the years, I learned at least a little bit from Rick. Not because hey, I mean, he's a great teacher, right? He's holding the chair for excellence in teaching, I think, something like that. Also, okay. Anyway, so today in his final talk, we'll talk about higher dimensional issues arising from gravitational theory. Let's welcome.
Well, thank you, Bo. So I'm going to do this without the microphone. I hope everyone can hear me. Okay. Oh, there's a fan noise, right? Okay, well, I'll try to speak up. There didn't seem to be a microphone available. So, okay, so thank you for sticking it out for 3 lectures. That's above and beyond the call of duty. I'll try to entertain you as much as I can, although there's a limit to what I can do. I'm not an entertainer really, but I sort of decided to give an overview of some rather broad areas related to the subject, rather than go into very much detail about proofs, some of which are very technical. So I'm going to start with the positive mass theorem, and I'm going to show how it's connected to some other problems in what you might say pure Riemannian geometry, questions about compact manifolds and the sorts of metrics they admit, the curvature properties that they could have, and so I'll lead up to that, and then there's an issue, the higher dimensional issues. Actually, there are many higher dimensional issues in this area. It's interesting that the dimension plays such a big role in several aspects, but there's a particular one which has to do with the proof of the positive mass theorem in high dimensions, which is related to singularities again. So it's the same word, singularities, but in this case they're singularities in hypersurfaces. That is submanifolds of the initial data set. And so let me begin with a quick review of the positive mass theorem. So remember, as we described in the last 2 lectures, the space-time is determined, assuming it's a predictable one, by an initial data set. And so we're going to study initial data sets. So those are n-dimensional manifolds. They have a given data, which is a Riemannian metric, and a tensor P, which is a symmetric 0-2 tensor. And I'm assuming everything is smooth, so there's no singularities in the data. And these satisfy certain restrictions, which are conditions on G and P. And so remember, those come from the Einstein equations and properties, basically the positive energy density properties of the matter, the stress energy tensor. And so the constraint equations, remember, were these 2. This is a scalar equation. So mu is a component of the stress energy tensor. It's T00, the observed energy density. And J, which is the divergence of this tensor pi, which is directly constructed from the second fundamental form, that's the momentum, the observed momentum density for an observer moving normal to the hypersurface. Okay, and these 2 quantities, which are expressed entirely in terms of G and P, they depend just on G and P, they satisfy an inequality. And so the inequality says mu is bigger than or equal to norm J. And in the particular case, when P is 0, it reduces to non-negative scalar curvature. And so basically the vector, the space-time vector with time component mu and spatial components J, is a is a forward pointing, that is mu is positive, and it's time-like. So that means the time part dominates the spatial part. Okay, and so that's what the dominant energy condition tells us. So that's the condition. And then we also have sort of boundary conditions, namely the asymptotic flatness. And so the requirement is that the initial manifold looks like Euclidean space near infinity. So, and that corresponds to the space-time looking like Minkowski space near infinity, asymptotically. And I'll give a precise fall-off rate on the next slide, but the intuitive picture is you sort of, so a good way to think of it is you can think of taking a compact manifold and blowing up a point. So just like you blow up the sphere and you get Euclidean space, you can do it conformally. So you can sort of think in that way for this also. So you could think of compactifying this. It's a compact manifold minus a point, and the metric is chosen so that it's asymptotically Euclidean. And so it's important actually in relativity to understand the precise fall-off. Let me just move this cursor out of the way. It's important to understand the precise fall-off, and the fall-off that's needed, and this is almost the sharp fall-off that you can get, and in order to show that the total energy and momentum are finite, are well defined. And so the requirement is on GNP, of course, the dominant energy condition, which I was on the previous slide, and then the fall-off is that in suitable coordinates, the metric is Euclidean plus terms that go to 0 like mod x to the minus r, where r has to be bigger than n minus 2 over 2. So notice in the Schwarzschild metric, that number r is n minus 2. So the Schwarzschild is Euclidean up to terms of order r to the n minus 2. And so this is a much, much weaker fall-off to Euclidean than the Schwarzschild would have. And then the second fundamental form, being a derivative of the metric, should fall off one order faster. And so it's of order x to the minus s, where s is bigger than n over 2. So n over 2 is this number plus 1. Okay? And so, yeah.
Of the space-time or of the hypersurface?
So this is all, so now we're just dealing with the initial data. So, yeah, right. So the space-time is generated, but it won't play a role in what I'm going to say. Okay, and so and the requirement also is that the scalar curvature falls off at an appropriate rate. It has to be integrable, and so we can assume it falls off like minus 2s. So that would be bigger than n, and so it would be an integrable function on the manifold. And so under this condition, there's a well-defined energy, which will be called a mass in the next slide. But the energy is this asymptotic flux integral. And so I won't explain why this limit exists, but it's related to the constraint equations, and it's important that this scalar curvature falls off appropriately. Okay, and so there's an analogous definition of linear momentum, total linear momentum, which I won't write down, but it's an asymptotic integral involving the second fundamental form, little p. Okay, and that's a vector. You can think of these as, so at infinity there's an asymptotic Minkowski space, and so you can think of you can think of E and P1, P2 up to P3 as a 4 vector in the asymptotic Minkowski space. Okay, and so the general form of the positive mass theorem says that assuming the dominant energy condition, so that the energy flow vector is time-like, then the total energy is also time-like. So in particular, the energy is non-negative, and the total energy momentum vector is time-like. So in this case, we can define. So technically, when you have linear momentum, the mass and the energy are not quite the same. So it's actually the Lorentz length of this vector, and so that would be the mass. And so in particular, the mass would be non-negative. And then the borderline case, which is rather subtle in the general case, is that the mass is 0 only if this can be isometrically embedded into Minkowski space. So in other words, it doesn't say that the data is trivial. It only says that it can be embedded into Minkowski space, so the space-time is flat. So the evolved space-time would be Minkowski space. Okay, and so I'm only really, because the general case is rather technical, I'm only going to discuss the case when P is 0. So in that case, the assumption is non-negative scalar curvature, and in that case, the mass is equal to the energy, and equality implies that this is isometric to Rn. And so I'll just discuss that case. And so in particular, the theorem we're interested in is this. So I have a manifold asymptotically flat in the sense described on the previous slide. So there's no P is 0. Scalar curvature is non-negative, then we have non-negative total mass, and it's 0 only if it's isometric to Rn. So it's a trivial data set. Yeah, so little p is the second fundamental form of the data. It's part of the initial data. Capital P is the total momentum. So the momentum, so little p determines it determines, let's see, let me say this right. Yeah, so it determines the momentum density locally, right? So if you remember, going back, the momentum density of the matter is this quantity, right? That's the observed momentum density. So in other words, an observer in space-time will view the matter as moving in some way. So it's not stationary. And so the matter has an energy density, and it also has a momentum density. And so the little p determines the momentum density. So this pi is just algebraically related to little p. Okay, where capital P is the total quantity. It's the total momentum, total linear momentum. Okay. Okay, and so now I want to come to one of the approaches to understanding this theorem, and that has to do with hypersurfaces, studying hypersurfaces in M. So remember, M is now a Riemannian manifold, and so if we look at a hypersurface, then we'll be interested in minimal hypersurfaces. And so the word minimal here means that the mean curvature is 0. So that means the trace of the second fundamental form is 0. I'm calling H here the second fundamental form. And so it has a variational interpretation. So let me, instead of writing a formula, let me just explain it variationally. So it says if you take your hypersurface, and I have a chalkboard here. So if you take your hypersurface and you deform it by an amount which is a function times, so we take a vector field which is a function phi multiplied by the normal. So we think of deforming the hypersurface in some direction where the amount we deform depends on the point that we move. And then we ask, let's assume phi is compactly supported so we don't do anything outside a compact set. Then we ask, how does the volume change when we do that? And so the mean curvature gives us the answer to that. So if we compute the volume, which I'll just use absolute values for that, then if I compute the rate of change at time 0, the infinitesimal change, it turns out to be minus the integral of h times phi, where h is the mean curvature. So in other words, the mean curvature vector gives us the direction or the speed so that the volume decreases at a maximal rate. Okay? So it's something like the gradient of the volume functional minus the gradient. And so in particular, you can see that the vanishing of h is equivalent to the condition that the volume is stationary under all deformations of sigma. Well, I've chosen normal deformations, but actually tangential deformations just correspond to reparameterization, so they don't change the volume. So it's sufficient to consider normal ones. And so in particular, this suggests we can construct such hypersurfaces by minimizing volume in an appropriate class. And indeed, that's what we'll consider. And so the minimization problem for volume is called the Plateau Problem, and actually it's a problem that Radó worked on. These lectures are named after. And so the Plateau Problem is the problem of minimizing among surfaces with a given boundary. And so if we're interested in, whereas if we're interested in constructing closed surfaces like we will be later, then a good class to work in is a homology class. Okay, and so that means that if we take a hypersurface, let's say it's compact, and suppose the hypersurface doesn't divide. That means when we cut the hypersurface out, the manifold's still connected, right? So that would represent a non-trivial integral homology class. Then we can look at all hypersurfaces that are homologous to that. So that means the hypersurface sigma naught, the one we started with, and the competitor bound to volume between them. So it might be a signed volume, but they're the boundary of a region. And so it turns out to be a good class in which to minimize volume. So it's sort of the natural Plateau problem for compact submanifolds of a Riemannian manifold. And so I should say that in the three-dimensional case, when the surfaces are two-dimensional, you can do some more refined constructions, minimize in some more restrictive classes. But in higher dimensions, geometric measure theory allows us to solve the problem in this class of homology. And so this is, it's a little hard to see, but this is a picture of a solution of the Plateau problem. So this blue is a wire, a closed wire, and it's dipped in a soap film, and the surface of least area that spans that curve, it will be a minimal surface if you neglect the weight of the soap solution, and so it will achieve the minimizer for the problem. Well, it will achieve a minimizer. You can construct curves where there's more than one as well, and so it's a rather interesting and complicated variational problem, which is also a physical one. It's related to, I mean, it's a fluids problem really. Okay, and so this is a picture just to give you an idea of the homology setting. So this is just the boundary surface is a torus, and we can look at it. If we look at a curve that goes around the handle, then that curve does not divide. So if I cut that curve out, the result is still connected, and so then I can look at curves that are homologous to that one. So that means they bound a region in between them. Well, in this picture, homology is really the same as homotopy, but in general they're of course not the same. And so then we can minimize volume, and what we produce is a geodesic, that is a shortest curve that goes around. Okay, and the same general idea works in higher dimensions as well.
So
yeah.
I just heard you say that in order to decrease the volume when you do this cutting, but in order to extremize the volume, the cut that you have to make is a geodesic? In the curve case, yeah. So a one-dimensional minimal surface is a geodesic. Yeah. And you can imagine that this is a three-manifold, so that could be like S2 cross S1, and then the S2 would be represent a homology class. Then I would have to minimize the area, and then I don't get something which is totally geodesic. I get something which is minimal. That means on average the principal curvatures. Well, for a geodesic, minimal is the same as the curvature being zero. Yeah, so the mean curvature of a curve is just the geodesic curvature, and so it vanishing means it's a geodesic. But in higher dimensions, there are, on a surface, there are two principal curvatures, and the mean curvature is the sum of those. And so it only means that the sum is zero, right? So it means that it's a saddle surface. One goes positive, one goes negative. Right? And that's the idea. You can sort of see that on this picture. You can see that it's a saddle, right? There's one curve going this way, and then the other one going the other way. So minimal surfaces are always saddle surfaces. They have negative Gauss curvature in general in R3. Okay, and so I wrote this formula down last time, and I think since you're all asking questions, which is good, I think I'm going to skip the derivation. So again, I skipped it yesterday too, so I can be consistent and skip it today. So the thing that's really important, and the way that the ambient manifold, the geometry of the ambient manifold affects the minimal surfaces is it can't be seen in the first order effect. It's a second order effect. So
curvature involves two derivatives, right? So the curvature, just like the curvature affects separation or focusing of geodesics, for minimal surfaces, it affects the question of whether the minimal surface tends to minimize volume or not minimize it. And the way that works is through a formula, which is it's the second variation formula. So this is really del 2, the second derivative of volume when I do that same variation. And so that turns out to be a quantity that looks like this, which I wrote down also yesterday. And so here I can allow any function phi which is compactly supported and sufficiently smooth. C1 or Lipschitz would be okay too. And so this quantity, I called it A yesterday, I want to write as h squared, the square length of the second fundamental form, or the sum of squares of principal curvatures of the hypersurface. Okay, and so again, this is an eigenvalue condition. It's equivalent to the lowest eigenvalue. This operator is called the Jacobi operator, and it's really the linearized mean curvature operator. So the mean curvature is a nonlinear function on hypersurfaces. When I deform, if I take a family which deforms, then I can linearize at the initial point, and when I do, I get a linear operator on the surface, and that's this operator. It's called the Jacobi operator, and so that's the eigenvalue condition. I could write this as minus phi Laplacian phi, and then it means that the operator minus L has a positive spectrum. So non-negative spectrum. The eigenvalues are non-negative. Okay, and so that's the nature of stability. And then as we said last time, this quantity, reach nu plus h squared, can be rewritten. And I think I'll again omit the expression. So the answer is that it's this. So it initially involves the Ricci curvature, and so it looks like the theory has to do with Ricci, but you can actually express it as a difference of scalar curvatures. So this is the scalar curvature of the ambient manifold, which we assume to be positive. And R sigma is the intrinsic scalar curvature of sigma. Okay, so it's the induced metric on sigma makes sigma a Riemannian manifold, so it has its own Riemann curvature tensor, and then the scalar curvature of that is R sigma. And there's still an extra second fundamental form term there. So notice half of them, there was a factor of 1 there, and there's only a factor of a half there. So half of it went away, but there's still a good positive term. And so the stability inequality then becomes this for arbitrary compactly supported phi. And we observed yesterday that in the three-dimensional case, when sigma is a surface, this has an immediate consequence, namely that I could choose phi to be 1 if it's a compact surface. And then and if I assume Rm is positive, then this is negative Rm, and this is minus that is negative. And so what I end up concluding is that the integral of R sigma is positive. But R sigma is the Gauss curvature, or really twice the Gauss curvature with the usual normalizations. And so we can use the Gauss-Plane theorem to then say that the Euler characteristic of sigma is positive. And so the only two closed surfaces with positive Euler characteristic are S2 and RP2. And so if it's orientable, then it has to be S2. Okay, and so that's an immediate consequence. So the statement is that if I have a three-manifold of positive scalar curvature, then any stable oriented hypersurface, which is two-sided, would be homeomorphic to S2. Okay, so that's an immediate consequence. Okay, so it looks like a two-dimensional or three-dimensional theorem, but actually it generalizes to higher dimensions in a very nice way, and let me explain that. So this is this was done with Yao actually a long time ago. It extends this idea to all dimensions. And so the statement is that if I take a closed stable hypersurface in a manifold with positive scalar curvature, then the hypersurface itself also has a metric with positive scalar curvature. So the basic idea of the stable hypersurface method is that the scalar curvature properties of the ambient manifold are inherited by the hypersurface, and we can cut down the dimension, so we get down to something we can understand, in particular like 2 or even 1 dimension actually, in some of the arguments. So in particular, this in the three-dimensional case is just the statement that we made before. Okay, but this is independent of the dimension. It's true for for any dimension. And the proof is, so you can't just use the variation phi equals 1. You have to use the fact that this is really an eigenvalue condition. And so, so the observation is that if the scalar curvature Rm is positive, and if I assume n is at least 4, then the eigenvalue condition implies, well, this inequality is actually obvious because this number here is less than 1, right? So for any n, that will be smaller than 1. And so the first term here is, this is a factor of 1 times grad phi squared, and so it dominates that. And the other terms are just equal. Well, not equal, but I threw away the Rm term, which is positive, and I threw away the h squared term, which is positive. So those give me negative contributions on the right. So in particular, I get this inequality. And now this quadratic form actually is a very important one in conformal geometry. And in particular, it implies that the lowest eigenvalue of this operator, LC, which is related directly to the previous one, but it's a different operator. So there's a constant there that this is the constant in dimension n minus 1, actually. And so this operator is called the conformally invariant Laplacian. So it turns out that if you conformally deform the metric, then the scalar curvature changes by a quantity which depends on this operator applied to the conformal factor. And so this operator has a natural conformal invariance, and having positive lowest eigenvalue for minus LC is equivalent to the condition that the metric of sigma can be conformally deformed to positive scalar curvature. So that's the higher dimensional generalization. So in 3 dimensions, we said that a stable hypersurface either S2 or RP2. Well, those surfaces can both be, for any metric, can be conformally deformed to positive Gauss curvature, and so the same thing is true in higher dimensions. And so there's the word for this is Yamabe positive. So this is related to the Yamabe problem. So in general, a conformal class of metrics is either Yamabe positive, 0, or negative, just like surfaces. There's either a metric of positive Gauss curvature, 0, or negative, and a similar thing is true. And this operator is the key to understanding that. And so in particular, the way the stability is used is it tells us something about the conformal class of the hypersurface that we choose. And so in particular, we get this result that if we started with positive scalar curvature, we choose a stable hypersurface, then it also has positive scalar curvature. Okay. And so there are a lot of consequences of this. So actually, we use these ideas to analyze compact, non-simply connected manifolds with positive scalar curvature. We gave a proof of the positive mass theorem up to dimension 8 using this. And so the dimensional restriction in this argument arises because minimizing hypersurface can be singular. So there's a singularity issue that occurs. So oddly enough, and for reasons that nobody understands as far as I know, it can happen. It happens in high dimensions, starting in dimension 8, that when you solve the Plateau problem or this corresponding homology problem, your minimizer may actually not be smooth. There can be a small singular set that occurs. And the singular set in general is, so in dimension 8, the 7-dimensional hypersurface can have isolated singularities. In dimension 9, you could have a 1-dimensional singular set. So in general, the singularities are a codimension 7 set. They're a closed set of Hausdorff codimension 7. Again, we don't know much about the structure. In fact, there are recent results which show the structure can be very arbitrary, actually. Leon Simon has a recent paper. Yeah.
The positive mass theorem for dimensions, say, greater than 3 or 4, are you implying thereby that there is an Einstein field equations for these higher dimensional cases?
Yeah. So we're just using the same equation, right? So the Einstein field equation makes sense in any dimension. And so if you like, it's a mathematical extension of relativity, but string theorists do look at higher dimensional gravity. So it does come up. But you can ask the same questions in higher dimensions as in 4 or 3. Okay, and so again, to summarize, the positive mass theorem holds for general asymptotically flat manifolds in dimension 8 or less, and for spin manifolds of any dimension. So I mentioned the Dirac operator yesterday, and so that actually gives the positive mass theorem in any dimension, but it requires the manifold to be spin. That's a topological condition on the manifold. And so actually, in recent work, we removed the dimensional restriction, but it's a pretty complicated technical thing. So I'll sketch that a bit at the end, but I don't want to go into too much detail because it would be hard to understand. So let me just say a little bit about singularities and some of the issues that come up here. They'll probably remind you a little of the singularity theorem that I spoke about in the first talk. But so the Plateau problem, of course, goes back hundreds of years, but it was first successfully solved only in the 20th century. And in particular, the two-dimensional problem was solved around 1930 by Douglas and Radó. Radó is given credit for, in fact, the solution we learn in graduate school is actually Radó's solution. Courant also simplified the solution of the Plateau problem. And then the higher dimensional problem was formulated through geometric measure theory, which was developed over the years and finally solved by, well, actually there are different versions, different classes solved, but the most efficient one seems to be what are called integral currents, and those were defined by Federer and Fleming in the early 60s, and they solved this homology problem that I mentioned, the Plateau problem. But then there's an issue of whether the minimizers are smooth or not. There's a regularity theorem, and that's what comes up here. And so let me just say that so the problem is that in high dimensions these can be singular. And so if I take an n-2 dimensional boundary in Rn and I solve the Plateau problem, then one can ask whether the singularities actually are stable in the sense that suppose I perturb the boundary, do the singularities remain or might they just go away? And actually nobody knows the answer except in dimension 8, that is in the lowest dimension, they actually can be made to go away. So there's a paper done by Hart and Simon which says that in the 8-dimensional case, if you have a singular solution, so actually singularities never occur at the boundary, they occur inside, and they're isolated points, you can always perturb the boundary a little bit to a nearby smooth boundary and get a regular solution. Okay? And so that's a kind of generic regularity result. Okay, and so and that was generalized by Nat Smale to the corresponding homology problem that I mentioned. So you can ask a similar question. Suppose I take a homology class alpha, so that's just represented by a given non-dividing hypersurface, sigma naught, and then all hypersurfaces homologous to that would be the class alpha. And then if you choose a metric, then of course you produce a volume minimizer in that class. And so you can ask the question, suppose a volume minimizer has singularities for a given metric, can I deform the metric a little bit to make a volume minimizer for the new metric smooth? And the answer to that is also yes, in 8 dimensions. So this is a result of Nat Smale, based on a similar idea as the Hart-Simon. It's a bit more subtle. So it's not known if such results hold in higher dimensions, but if there were such a generic regularity result, the minimal hypersurface method would extend to all dimensions. So it's sort of interesting that if there were a counterexample to the positive mass theorem in some high dimension, it would actually imply that there are singularities which are stable, which can't be removed. But on the other hand, I'm claiming there is no counterexample. So that's a sort of just a thought experiment. Okay, and so right. So that's an open question as to whether singularities might be. You might have generic regularity.
Does the fact that this holds for n is equal to 8 have anything to do with octonians? There are quaternions,
not directly. I mean, so the reason is because, so the idea is that in dimension 8, the singularities are isolated. And the singularities locally look like cones, so they're tangent cones at the singularities. And what happens is if you push off to one side of the cone, the surface becomes regular. And so the idea of this Hart-Simon paper is to do a deformation which forces you to make a one-sided push near the singularities, and then then it becomes regular. So maybe the question is, does the fact that singularities exist in dimension 8 have anything to do with it? And you know, there are explicit examples of cones which are singular at a point, which have been shown to minimize volume. And so they're simple quadratic cones. It was found by James Simons before he made all his money. They're simple quadratic cones. They're just solutions of a quadratic polynomial. So in R8 is just the cone x1 squared up to x4 squared is equal to x5 squared up to x8 squared. So it has topology in this. The link is topology S3 cross S3, and the cone over that turns out to be volume minimizing. So you can do the same construction in lower dimensions. You get minimal cones, but they're not minimizing. And so why do singularities occur in that dimension? It's a computational thing. And again, it would be nice to understand it from a more sort of intuitive point of view. Okay, and so let me now explain why the positive mass theorem has something to do with compact manifolds with positive scalar curvature. And so the idea is, so remember that the Einstein equations are a system of wave equations. Okay, and so if you think about the ordinary wave equation just in flat space, if you pose initial data in a space of functions with suitable decay so that the energy, say the potential and the kinetic energy actually are finite, then it would be normally true that the compactly supported data would form a dense subset. And so often if you want to prove a statement about energies, it's really enough to consider compactly supported data. And so one of the difficulties in proving the positive mass theorem is the asymptotics are quite complicated. You could, for example, ask whether there's something similar for Einstein data for the Einstein equations. And so it doesn't directly generalize because, of course, there are no non-trivial manifolds. So being trivial outside a compact set would mean the metric is Euclidean and the second fundamental form is 0, right? And so there are no such manifolds with non-negative scalar curvature, and that's a consequence of the positive mass theorem. So it doesn't really work. You can't simplify the asymptotics to the simplest form you might like, but you can still ask whether whether metrics with asymptotics of a special form are dense in the space of asymptotically flat metrics. And so that turns out to be true. And there's a nice form which actually Yao and I developed this in the initial proof of the positive mass theorem because we were assuming some special properties of the asymptotic. So a useful form in this case is that you could ask that the metric be conformally flat near infinity. So for example, the Schwarzschild metric we saw was actually a function times the Euclidean metric. So it was conformally flat. So in particular, we might ask whether we could write the metric as u to a power. This power is just there for convenience of formulas, which we'll see in a minute, and times the Euclidean metric. So the metric is the same inside, in compact parts, but we just simplify the asymptotics. So we could ask whether solutions with conformally flat asymptotics. And so we could also require 0 scalar curvature near infinity. Then that's equivalent to the function u being harmonic. So again, it's related to this conformal Laplacian that we solved. If you take the scalar curvature of that, it turns out you get something involving the conformal Laplacian, which in this case is just the Laplacian. So u is actually a harmonic function near infinity, which is asymptotic to 1 because we're asymptotically flat. And so in particular, it satisfies Laplace u is 0 and the limit is 1. And so a function like that has an asymptotic expansion. So the leading order part is just the conformal factor that gave us Schwarzschild, right? And so it's really Schwarzschild plus lower order terms. And so you get this. And in particular, the m there is the ADM mass of G. And so you can ask, let's look at all initial data. which have non-negative scalar curvature and which have conformally flat asymptotics. Then you can ask, can any initial data set be approximated by one of those? And the answer turns out to be yes. So in fact, as I said, we developed this a long time ago. So in particular, the metrics with conformally flat asymptotics and non-negative scalar curvature are actually dense in the space of all asymptotically flat metrics with the asymptotics that I described in the beginning. And moreover, the mass is a continuous function in the natural topology which encodes the decay. And so in particular, if we had an initial metric with negative mass, say, I could approximate it by one with very nice asymptotics, which also has negative mass. Okay, and so it enables us, at least for detecting approximate properties of the mass, to assume this sort of asymptotic form. And so that's the first step. Then there's a further observation which is done somewhat later by Locamp. And his observation is that if the mass were negative, then you could do a simple modification of the function u to deform the metric to be exactly Euclidean near infinity, and keeping the scalar curvature non-negative. So it's quite easy to do. It's so the function u is harmonic. The non-negative scalar curvature is equivalent to the function being superharmonic. That is, Laplacian u is less than or equal to 0. And so if m is negative, then this function approaches 1 from below. And so the idea is just you can take the function going up near infinity and cut it off and make it constant. And then when you do that, you get a corner. But that, if you smooth it out, you get something superharmonic. So it's a very simple, really a very simple construction. And then once u is constant near infinity, then that's the Euclidean metric. Even though the constant might be a half, you can just change coordinates, and it's isometric to Euclidean. Okay, and so so that's the other observation. And so what that enables us to do is something quite convenient. Namely, it enables us to compactify the problem. And so in particular, if the metric's Euclidean outside a compact set, we can enclose the non-flat part in a box. So suppose I have a metric which has some complicated structure in here, but it's Euclidean out here. I can just put a big n-dimensional cube around it, and then I can just translate the metric and make it periodic. So I can make it periodic, and what I get in the quotient, and then when I take the quotient by the group z to the n, I get a compact manifold. Well, if I started with Rn, then it would be topologically Tn. If I started with some other manifold, then in general, then it would be a connected sum, Tn connected M0. So what you can think of doing is just surrounding this non-flat part by a sphere, and then that's just a picture like I was drawing before. So the quotient would be Tn, and then I think of my sphere as small, and then this is M0, which is some other manifold which we don't know. So M0 is so in other words, the original. You could say it another way. So if you think of the original asymptotically flat manifold, you could compactify it, just the one-point compactification. That would be M0. And so when you do this, if you had such a metric, you would produce a metric of non-negative scalar curvature, which is not flat, on this manifold. A specific manifold, but M0 could be anything. So the only thing we know about M0 is it came from this. It has non-negative scalar curvature. And so, so in particular, if we could show that this manifold Tn connect M0 for any compact M0 does not carry a non-flat metric with non-negative scalar curvature, then we could prove the weak positive mass theorem following this line of reasoning. Namely, we could prove that M is non-negative. So the argument would be if M were negative, then we could make the metric Euclidean near infinity. We could then do this periodic construction. We would produce a non-trivial, non-flat metric on a manifold of this type. Okay? And then also, we might call this the weak positive mass theorem. The borderline case when m is 0 can actually be derived from this without too much trouble. So there's a sort of a perturbation argument for showing that if you know the weak positive mass theorem, you can actually you can prove that if M is 0, then the manifold's Euclidean. Okay. So that's sort of independent of the arguments for the positive mass theorem. Okay, and so in particular, it leads to this question of understanding compact manifolds with non-negative scalar curvature. And this is also a very interesting question in Riemannian geometry. So you can ask which smooth compact manifolds can carry metrics with positive scalar curvature. And of course, for n equals 2, the answer is S2 and RP2. So you can prove this in various ways, but maybe the Gauss-Plane theorem is the simplest. You have to assume, of course, the classification of surfaces. Okay, and for n equals 3, the complete list is also known. So it includes S3 and its quotients. Those are called spherical space forms. They're like lens spaces. There are some others that are not lens spaces too. The Poincaré homology sphere is an interesting quotient. And then S1 cross S2 has positive scalar curvature, and it has a couple of quotients. You take like S1 cross RP2, and there's another quotient. So those have positive scalar curvature. And then the other ones are connected sums of these. So you can take any finite collection of compact 3 manifolds with positive scalar curvature. You can form their connected sum. You can join them up like you form a homogeneous surface out of tori. And they all also have positive scalar curvature. And that's all. So much of this can be proven using minimal surface theory, somewhat more refined than I've talked about. But it does require at the end an assist from Ricci flow. So I don't know of any proof that a potential homotopy sphere might not have R positive. So in other words, even assuming R is positive, I don't know how to prove. I don't have a direct proof of the Poincaré conjecture. So that follows from the Ricci flow, which proves that a homotopy sphere is actually a standard sphere. Okay, and so let me say a key part of this is to remove. So there's actually a general theorem in 3 manifolds that every closed 3 manifold can be written as a connected sum of prime pieces, and so it's a matter of understanding what the pieces can be. And so the key argument really is to rule out what are called k-pi1 3 manifolds, like a torus or a hyperbolic manifold, things like that. A k-pi1 manifold is one whose universal cover is contractible. And so it means that that pi1 would be infinite, but the higher homotopy groups are 0. So the universal cover is actually a contractible manifold. In the 3-dimensional case, it's actually known to be R3, I guess. Yeah, and so that's a key part of the argument. And so let me just say, in dimension n greater than or equal to 4, there are many open questions concerning this, but there's actually a beautiful theorem for simply connected manifolds in high dimensions. It's essentially a topological theorem, but it was conjectured by Gromov-Lawson, proved by Stoltz in the mid to late 90s, I think. And okay, so it has to do with the Dirac operator. So recall from I think it was the first talk, that positive scalar curvature implies the Dirac operator has no kernel, no non-trivial kernel. Any harmonic spinor that is a solution of the Dirac equation actually vanishes because of the positivity of the scalar curvature. And now, and so in particular, the index of the operator. So the index is the kernel, dimension of the kernel minus the dimension of the co-kernel. So in particular, the index is 0 for the Dirac operator. It's always a non-negative number. And so, so it's 0. And this has topological consequences from the Atiyah-Singer index theorem. So Stoltz proved the converse of this, essentially. So that if you take a simply connected manifold of dimension at least 5, then in fact, if let's assume it's spin, so assuming it's a spin manifold, you can define the Dirac operator, and then he proved that if the index of the Dirac operator is 0, then the manifold does have positive scalar curvature. It carries a metric with positive scalar curvature. And Gromov and Lawson had already shown that in non-spin manifolds, if you don't have the spin assumption, you automatically have positive scalar curvature, and again, for simply connected manifolds. So it's quite a remarkable thing in that if you take a high-dimensional, simply connected manifold, you can in principle say whether or not it has a metric of positive scalar curvature. It's a very rare thing in Riemannian geometry to be able to give a complete classification of curvature conditions like that. And so in particular, you could say that the Dirac operator gives all the topological information, at least for high-dimensional, simply connected manifolds to have positive scalar curvature. And so in the case of non-simply connected manifolds, a classification is probably hopeless, but one could expect that a k pi 1 manifold of any dimension cannot carry a metric with positive scalar curvature. And again, k pi 1 manifolds examples are manifolds of non-positive curvature, but there are many others also that are not non-positively curved. So actually in the three-dimensional case, we proved that a long time ago. But within the last year or so, it was proven in dimension 4 by Otis Chodash and Chao Li. And shortly after their paper was posted, the method was extended to dimension 5. It was done by them and also independently by Gromov. Gromov is very interested in scalar curvature right now. And so the proofs involve modifications of the minimal hypersurface method, which deal with issues related to the non-compactness of suitable coverings. So the proof works in some non-compact covering. And so you have to allow, and so that causes problems with when you minimize volume, because things may run off to infinity, may be complicated near infinity. So you have to handle that kind of issue. And it turns out there's a modification of the volume functional which does that. And so, but so far it's restricted to dimensions 4 and 5. So that's some recent work. And let me just say, I'm almost out of time, but I think I have time just to say a little bit about higher dimensional singularities. And so higher dimensional singularities which occur on higher dimensional hypersurfaces. So let me just say in a very superficial way what happens, the regularity theory for minimizing hypersurfaces. So if I take sigma to be a minimizing hypersurface in M, then in general there's a closed singular set which is defined as the complement of the regular set. So the regular set is points regular if there's a neighborhood in which the surface is smooth near that point. And so in particular the singular set is a closed set by definition. And so a basic consequence of the theory is that at every singular point there's a non-trivial tangent cone. So it's a volume minimizing cone. It's gotten by blowing up. So it's something similar happens for algebraic singularities, but it's gotten by blowing up the surface, and you can then show that you get a cone which also minimizes area. And then the cone, of course, might also be singular, but there are methods to cut down dimension to get to study regular cones. And so you can ask, in what dimensions do you have minimizing cones? And so those can be studied by geometric methods. The intersection of a minimal cone with the sphere is a minimal submanifold of the sphere, a compact one. And so this, in 1968, Jim Simons shows that there are no such cones in dimension less than or equal to 7. That is when the ambient space is dimension less than or equal to 7. It then follows from regularity arguments that for n less than 8, the singular set's empty, so they're actually smooth. And in general dimension, the singular set may be there, but it's a thin set, so it has Hausdorff codimension n minus 8. So it's a closed set, but it's not anything like a manifold necessarily, or even a complex. So and so the argument for proving the positive mass theorem requires slicing to low dimensions. So remember, the idea was that if we started with positive scalar curvature, we take a stable hypersurface that has positive scalar curvature. We then look at a stable hypersurface in that, and then we cut down to low dimensions. And so the difficulty is that if there are singularities in a slice, then the lower dimensional slices can hit the previous singularities, and it's very hard to say what's going on. I mean, the whole thing may become singular when you slice down low enough. And so you might lose control entirely of the regular set. And so the whole game here is to control the singularities of the slice, so not just of the full family of slices. And so the geometric objects that we consider are called minimal k-slicings. And so we can think of those as nested families of hypersurfaces. So sigma n minus 1 is stable in M. Sigma n minus 2 would be stable, but not for the volume functional, for a weighted volume. So the other thing that's important is that we also, remember, we only knew it was Yamabe positive scalar curvature. So we had to also multiply the metric by a factor. So there's a density that comes in. And so sigma n minus 2 would actually minimize a weighted volume. So sigma j minimizes a weighted volume in Vj plus 1. The weight function would be the product of all the previous eigenvalues. So the u's are the first eigenvalues of the second variation form, or actually you have to fiddle with the form somewhat to do it. So it's a rather technical thing, but the main result is that, so again, we can define a point to be regular if all of the slices are regular. So the lowest slice together with all the previous ones. So in other words, if you look at the tangent plane at a regular point of the slices, it just looks like a family of planes that are nested. It's like a flag of planes. And so again, that's an open set, and so the complement is closed. And so the key thing is, the key theorem says that we can control this singular set. So it never gets bigger than codimension 3. That's in the k-dimensional slice. So in other words, you don't have low-dimensional slices which fall completely into the higher dimensional singular sets. And so in particular, when k is 2, it's actually regular. And so the argument really involves cutting down to 2 dimensions. So in particular, everything works locally near this sigma 2, which is regular, and so we can do all of the basic arguments. We can prove sigma 2 is a 2-sphere, in other words, topologically. And so again, the main step involved is to show that at each point there's a non-trivial homogeneous k-slicing. So that would be a nested family of cones. So instead of just having one cone, you get a nested family, and the u's, the density functions, are homogeneous of some degree. So everything becomes homogeneous. So it's the idea, actually there's this general idea in geometry that when you have singular objects, when you blow up at a singular point, in good cases, the limiting homogeneous object is actually nicer, geometrically better than the original one. So that's true in Ricci flow. So the whole idea of controlling singularities of Ricci flow is that when you blow up, you produce these soliton or ancient solutions which look locally. You can classify them. So if you can classify the blow-ups, then you can say something. Well, here we can't classify the blow-ups, but we can show that you produce a non-trivial slicing, and we can show that there is no non-trivial homogeneous minimal 2 slicing. And so that comes from the eigenvalue condition coming from the stability operator. So the fact that there's no non-trivial 2 slicing tells us the singular set must have codimension at least 3. Just like Simon's theorem said there's no singularity up to dimension 7, that implies the singular set has Hausdorff codimension, codimension 8, I guess. And so, right. And so that's the basic thing. And so then I can roughly describe the proof of the high dimensional positive mass theorem. So if you look at this manifold, of course, it has very special structure. So for example, it has the n forms, the 1 forms, the basic 1 forms coming from Tn, and you can pull those back. So the manifold has a degree 1 map to a torus. So I can take the n basic 1 forms in the torus, I can pull them back, and I get n closed 1 forms whose wedge product is homologous to the volume form, or it's a non-trivial in cohomologous to the volume form. And so in particular, I can then construct a 2 slicing where the jth slice, the integral over sigma j is 1 for the jth slice. So the wedge product of the first j is is homologous to the volume form of the sigma j. So roughly it just corresponds to the slicing of Tn minus T, T2 contained in T3, contained in T4, contained in T5, et cetera. The natural sort of slicing of the torus as an increasing dimensional subtoric. Okay, and so in particular, when we get down to dimension 2, it's a smooth surface, and of course these forms cannot be exact on sigma 2 because otherwise the integral would be 0. But on the other hand, the scalar curvature condition tells us that the sigma 2 surface is S2 topologically, and so it doesn't have any closed one forms that are not exact. And so in particular, if M had positive scalar curvature, it would follow that it's homeomorphic to S2, and that's a contradiction. So that's sort of the idea of the proof. So the minimal hypersurface arguments all involve these slicings, the always cutting down the dimension. And there's a good reason for that, of course, because I could, if I take any manifold of dimension k and I cross it with S2, then I get a k plus 2-dimensional manifold. That always has positive scalar curvature, right? Because I can take the S2 to be very small, then that has very big Gauss curvature, and then it dominates any negativity that comes from the other factor. And so you cannot detect scalar curvature in you can't detect it in codimension 1 homology, or even, you have to go down to sort of low-dimensional objects in order to detect it. And so, okay, so that's the basic idea, and the construction, the fact that you can this regularity theorem and also the existence of the slicing in the presence of singularities is a fairly technical thing. So it's on the archive, and it's appearing soon, I think. So okay, so that's the end. That's all I have.
So are there any questions?
So you mentioned the different version of this positive mass theorem for several asymptotic flat manifolds, spin manifolds, etc. So I'm wondering, are there any physical meanings of the theorems?
Which positive? You mean in high dimensions, or?
Right.
So you're okay in dimension 3, right? So that's directly related to relativity. Physical meaning. Well, again, the question is asked in string theory. Now, whether string theory has physical meaning or not, I think it might be a matter of debate, but I'm not qualified to really debate that. But it's some very interesting mathematics, including this things like the higher dimensional gravity. And so the positive mass theorem does play a role in higher dimensions, not all dimensions, but certain dimensions in string theory. Beyond that, I don't know of any. Yeah, that's the only way I know in which higher dimensional gravity comes in. Of course, it's very natural mathematically, but physically, yeah, I'm not sure. Yeah.
Yeah, when we're talking about positive scalar curvature for non-simply connected things, and I know I used to always hear this stuff about higher A hat genus, right? The A hat genus was possessed by that.
So in the K pi 1 case in particular, or?
That's supposed to be, what's the conjecture supposed to be?
You mean for general manifolds? I've heard, I don't know, Gromov and Lawson might have discussed that. So it's something related to KO characteristic classes or something like that. But I don't know if there's a concrete conjecture for general non-simply. I think even if you have finite fundamental group, it's a very hard question to understand whether it has positive scalar curvature. The K pi 1 case is sort of the opposite extreme, where you expect that you don't have, I think. Yeah, for the in between, yeah, I just don't know offhand whether there's a concrete conjecture on that or not.
K pi 1 cases, so have I thought the conjecture was like coupling up with something.
Yeah.
K5 1 with the axes was like a local property.
Yeah, like the Novikov conjecture, right? Yeah. Yeah. I don't know whether that, I mean, that gives a statement, but it wouldn't give a classification, I don't think. Yeah. Yeah. That would be the starting point of that. Yeah. Right. Okay. Yeah. 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 So that's a hard question in itself. So it has been done up to dimension 5, but the higher dimensional case, it becomes more and more complicated because the surfaces, you have to understand, it involves, so it's sort of, the 4-dimensional case can be understood because if you take non-compact manifolds, surfaces in a 3-manifold with positive scalar curvature, then you can prove they look sort of like trees. So you can think of a tree and you can think of a neighborhood. So the neighborhoods are 2 spheres. So they have the property that when you intersect with a large ball, the boundary, you get boundary components which are 2 spheres, and so those can be locally filled in. And so you need to understand the structure of non-compact things. And that seems to become harder and harder as the dimension goes up, because you need to get it. You need to do it for the top dimensional, and then you need to slice it down like that. And so in dimension 4, the hypersurface is 3-dimensional, and we have some understanding of the sort of infinite behavior of those. Whereas that, when you get to higher dimensions, it becomes much harder to do that.
So you mean non-compact, also non-complete?
Non-compact. So the proof works in a covering of the original manifold for K-pi1. So you do something like you take the universal cover and you quotient out by a Z action. So you get a manifold which is non-compact and the fundamental group is Z, and then you want to construct a hypersurface which sort of links that geodesic, that circle. So the problem is the geometry can be quite complicated near infinity, and you want to be able to show that if the scalar curvature is strictly positive, say bigger than 1, you won't be able to construct such a hypersurface. So what happens in 3 dimensions, if you do that construction, you can actually bound the diameter of a stable 2-dimensional surface, right? And so you can actually show that you can't, you get an immediate contradiction. Now in 3 dimensions, that's because for surfaces, positive curvature bigger than 1 implies a diameter bound. For 3 manifolds, scalar curvature bigger than 1 does not imply a diameter bound. You can have things like, long, thin pieces like S1 cross S2. But on the other hand, you expect that you can sort of slice it so you do get diameter bounds. And then in higher dimensions, you have to, slice more and more. So that's the tricky part. Yeah.
So if you consider asymptotically hyperbolic space, so you have a similar, something similar, like the positive mass quantity. The quantity is similar to that.
Yeah. So there is a notion of so it's related to, in relativity, it's called Bondi mass. You can also measure the mass at null infinity, and so that involves studying asymptotically hyperbolic, and it's a little more complicated thing. It's actually directionally dependent. The boundary of hyperbolic space is a sphere, so it's actually sort of the integral of a function on the boundary. But yeah, these kinds of methods do work to prove the positivity. There are Dirac operator arguments, and there are also in that case they're actually constant mean curvature arguments, like they're sort of modeled on the horosphere in hyperbolic space. But there are theorems like that, and they do use similar ideas. So there would be similar problems with singularities in high dimensions for that problem. So the assumption would not be scalar curvature bigger than or equal to 0. It would be scalar curvature bigger than or equal to the scalar curvature of the hyperbolic space, which is minus n minus 1. So the model space there would be hyperbolic space. And so what you're saying is that if you have something asymptotic to hyperbolic space with larger scalar curvature, then near infinity, it has some deviation from hyperbolic space. So that's the idea of the positive mass theorem. If you have non-negative scalar curvature and asymptotically Euclidean, it can't approach Euclidean too quickly. So there's some limit to the rate of decay. And so there's a similar statement in hyperbolic space. And there are analogous arguments. They're all a little harder, of course, in hyperbolic space. This one's already hard enough, so I've kind of I kind of avoided that. But there are lots of papers on it, lots of work on it.
How about in the convex setting?
The sphere S2, SN?
Like
yeah, so you know, there were these conjectures about analogous results for SN, but they seem to turn out to be false. I mean, there's this Menu conjecture which claimed that if you take a metric on the upper half ball, which on the boundary agrees with the spherical metric, and the scalar curvature is bigger than the scalar curvature of the sphere, then it should be the sphere. So it turned out not to be true. I mean, it's true in some cases, but there's a counterexample in general. So yeah, the positive case, I mean, scalar curvature bounded below by a positive constant seems much more complicated than the flat in the hyperbolic cases. Yeah.
beautiful 3 lectures.
Okay, well, thank you all for coming.